Welcome back. So, we'll continue the discussion on this simple solution of this full flapping equation. We have looked at two situations. One case which is only rotation here, and which leads to coning, and then we have included hinge spring and the offset. Now, what we would like to include the gravity term. So, as soon as we include the gravity, so this actually complicates the solution. Okay. So obviously, like we have done in the other cases, we assume no yaw, no crosswind, no wind shear. Okay. Then the solution matrix that becomes K B0 2B K minus 1 gamma by 8 0 minus gamma by 8 K minus 1 beta naught beta 1C beta 1S get 2A 0 0. Okay. I mean, obviously, we can use Cramer's rule. So using typical Cramer's rule, we can find out the determinant. Okay. So that would be K minus 1 gamma by 8 K minus 1 minus B, which is 2B gamma by 8. So what it gives, the determinant is K minus 1 square plus gamma by 8 square minus 2B square K minus 1. So obviously, I mean, once you find the determinant, then like in Cramer's rule, one can find the desired values by substituting the right-hand side vector into the corresponding column of the matrix, and then finding the new matrix and dividing by the original determinant. So what will happen? Now the first term, that is beta naught, will have now sine and cosine of azimuthal angle. So the solution that one can get gamma A by 2D K minus 1 square by gamma by 8 square. Okay. So this is what you get. Now, similarly, you have beta 1C, which is minus B A by D gamma K minus 1, and beta 1S would be minus B A by D gamma square by 8. So here, since the cosine and sine terms are negative, the rotor disc is tilted downwind and to the left. So now this magnitude of the sine and cosine terms can be related by cyclic shearing. So the cyclic sharing would give beta 1s is gamma by 8k minus 1 beta 1c. So this indicates the relative amount of movement, integrates the relative amount of movement backwards compared to sideways. So for a rotor with uh, so for a rotor with independent freely hinged blade, rotor with independent freely hinged blade, that means K is approaching towards 1. So there will be mostly yawing. Okay. Similarly, for a tipped machine, there would be mostly tilting. This can also be considered in terms of phase lag. Also, if you recall, the gravity is a cosine input for flapping. For a stiff blade, the response is mostly a cosine response, so there will be little phase lag. For a tethered rotor, the response to a cosine input is only a function of the sine of the azimuth angle. That means the response has a 90-degree phase lag from the disturbance. Okay. So these are the outcome that you would have on. Now we consider wind shear plus hinge spring. So this again here one can ignore gravity, yaw, cross flow terms, etc. So that matrix becomes K00 gamma by 8, 0 minus gamma by 8, K minus 1, beta 0. So the determinant of the coefficient matrix from here, what we get is K into K minus 1 square plus gamma square by 8. Again, once you apply Kamat's rule, you can find out the solution. So beta naught would be gamma by 2 A by K, beta 1 C is minus 1 by D, gamma by 8 K nu S K into K minus 1, and beta 1s is minus 1 by D, gamma square by 8 K nu S over K. So what you have essentially, the wind shear is a cosine input. Okay. So if you recall, wind shear is a cosine input. In response, a steep rotor will have both cosine and sine responses. So in response, a steep rotor will have both cosine and sine responses. A tethered rotor with k equals to 1 will only have sine response. So obviously, if you see this, that means when you consider the wind shear, which is essentially a cosine input, it allows the turbine to respond to a different way. So steep rotor will have both cosine sine response, tethered rotor will only sine response, but wherever the turbine response would be both sine and cosine cyclic responses. So the turbine will have both cyclic responses here. So that would respond to both the cyclic patterns and all these things. Okay. Now, if we try to get a general solution or write down the general solution of flapping equation of motion. So simply, general solution one can find out just by using Kramers rule to the matrix. And then but that would not be very illuminating. So one approach that helps to add some clarity is to express the terms in the flapping angle as sum of other constant. So which contributes, which represent the contribution of the various forcing effect. So one can say beta 1c 1c crosswind, beta 1c yaw rate, beta 1c nu s. Beta 1s would be beta 1s ag, beta 1s crosswind, yaw rate 1s nu s. Here ag subscript is for axial flow, and hinge spring, and gravity, that is blade weight. Cr for crosswind, yr for yaw rate, nu s for vertical wind shear. Okay. So this is what one can represent the flapping angle as the sum of other constant. But one has to understand that each of these constants are also function of other parameters. So we can have this, instead of rather expanding the matrix solution by itself, we can present the various subscripted terms which could be obtained from such a solution. The dominant owning term includes axial flow, hinge spring, and gravity, which includes axial flow, hinge spring, and gravity. That can be said that beta naught 1 by determinant gamma a by 2 plus gamma by 8 square. So now if we put these things in a table, so like we have kind of an so this is AAG, CR, mu S, YR. We have cosine, which is beta 1 C star. You have sine beta 1 A star. So AAG is 1 by D gamma BA K minus 1 V naught by D gamma by 8 square gamma by 2 into 4 by 3 A minus gamma A3 by 2 K into K minus 1. Then this is minus KSH U bar by D gamma by 8 K into K minus 1. This would be K U bar by D gamma by 8 square minus 2K minus 1 gamma A3 by 2 into K minus 1 D bar yo. So these are cosine terms. Similarly, sine terms is 1 by D gamma by 8 BA plus by D V naught gamma by 8 square 4 by 3 A into K minus 1 plus A3K minus KSH U bar by D square into K Q bar by D gamma by 8 gamma by 2 A3 K plus 1. So these are contribution to flapping responses. Okay. So these are all cosine and sine terms which are kind of summarized. So what you can see that once we talk about the general solution, then I mean one can do that using that matrix by finding the determinant can find the complete solution, but it would be good to express this flapping angle in terms of different contribution. And these are the cosine and sine. So this is something quite interesting too. But one important point to note here is that about the various subscribed constant is that they can help to illustrate the amount of response that is due to a particular input. For example, in a particular situation, if the wind shear sine cyclic response were close in magnitude to the total sine cyclic response constant, that it would be immediately apparent from this system that the other factors were of little significance. So this table kind of suggests you to identify the dominance of the different inputs and their responses to that. Okay, so this is how you can have a solution to this different uh, terms and components of this. Now, along with this, once we find out the complete solution, so this is the complete solution of the flapping motion. So once we find out the solution to this complete system, then it is good to also look at the loads like blade and hub loads for this. So that one can determine by estimating the forces on the blades and the root and the hub. So good to know the blade and hub loads. So moments and forces on the hub and tower can be determined. So the moments and forces on tower and hub can be determined. Okay. So for a rigid rotor turbine with cantilevered and not tethered blades, both flapping and lead lag movements are transmitted to hub. So for a rigid rotor turbine with cantilevered and not tethered blades, both flapping and lead lag movements are transmitted to hub. Flapping is usually the predominant aerodynamic load, and then so in tethered rotor, on the other hand, no flapping moments are transmitted to the hub unless the tethered stops are hit. Okay. On the so what we can do that if you recall the blade flapping angle, which was approximated as beta 1 plus beta 1 c cos psi plus beta 1 s sin psi. So, so corresponding blade root bending moment for each blade can be estimated as m beta is k beta into beta. So this is what one can estimate. So I mean, so if you look at the hub reactions, and then you have tethered rotor, and then you have cantilevered. Then you have flapping moment, flapping shear, lead lag moment, lead lag shear, blade tension, blade torsion. So this case it would be none. This case would be total thrust on hinge. This case it would be power torque. Then this case would be force producing torque. This case centrifugal force, weight. This case would be pitching moment. It would be full flap movement, full flap movement, thrust of each blade. This is power torque, force producing torque, mm, centrifugal force, weight, one blade pitching moment. So, in similar to the development of the flap equation, one could develop a lead lag and torsion equation and full set of response to get hub loads and all these things. So this give you an idea about those things. So then top of that you can have, tower loads. Okay, so tower loads can come from multiple fronts. One could be from aerodynamic load, aerodynamic tower load. Then you can have tower vibration. You can have dynamic tower loads. Okay, so all this you can have. So essentially, the aerodynamics tower loads include the rotor thrust during normal operation, the moment of the rotor torque, extreme wing load, uh, then tower natural frequencies can be estimated. Then the most important concept in the tower design is to avoid natural frequencies of the rotor frequencies like 1P, 2P, 3P. Then dynamic loads on the tower during. So all these, then I mean, the in dynamic tower loads you can have the different flap wise these things. So now you can have yaw stability. So yaw stability is an issue for few yaw turbines. This complicated problem and simplified dynamic model is of limited utility in its analysis at this moment. But it can provide some insight to some of the basic physics. The first thing is to note that both vertical wind shear and gravitational force on both blades, and on the bent blades, tend to turn the rotor out of the wind in the same direction. This means that the rotor tend to experience a crosswind from the direction, rotor back in the other direction. For yaw stability, then, mm, for yaw stability, if gravity steady wind, uh, wind shear are only effects considered, then the beta 1s ag plus beta 1s nu s. So using this and ignoring the wind shear and assuming small approximation, one can find steady state yaw error, which is uh, that is omega r by v 3b by 2 into 2k minus 1. So the steady state yaw error, then in the absence of vertical wind shear, is greater at faster rotor speed. Okay, and softer rotors, which is smaller k, vertical wind shear here, if you see this expression, the vertical wind shear would increase the steady state yaw error even more. Obviously, one needs to carry out a thorough analysis of these terms. So, I mean, you can see this when you talk about this mechanics and the dynamics and of this all these things. So, you have these are giving these simplified systems gives you the mm, uh, find out the analytical solution for estimating the initial design parameter. So this pretty much gives you the complete picture of the dynamics of the wind turbine. And there are few points which we will discuss in the next session to continue. Okay, thank you.